I'm going to show you now an alternative way to build a motor start-stop program using PLC. Right here I have an Allen Bradley Micrologix 1000 PLC, a series of toggle switches wired up to the inputs. I'm going to use this as my trainer unit as I demonstrate the operation of this motor start-stop program. First, I want you to notice we have a start contact and a stop contact. Remember that contacts in PLC ladder logic programming represent read instructions. So this contact is reading the status of input element 0 bit 0. This contact here is reading the status of input element 0 bit 1. In each of these cases, the contact runs over to a separate coil, but the coils themselves are different. These are not the normal OTE output instructions. They are latch and unlatch coils. The way this works, the way all coils work in PLC programming, is a coil is a write instruction. It's going to be tasked with the responsibility of writing the status of a bit in the PLC's memory. But the latch and unlatch coils work a little bit differently from normal coils you're familiar with. With a normal coil, when imaginary power is sent to it, it writes a 1 to that bit. And in a normal coil, when the imaginary power stops, that coil writes a 0 to that bit. In this case, the latch and unlatch coils are what we call retentive instructions. So what they do with regard to the imaginary power sent to them is a bit different. The latch coil will write a 1 to this memory spot when it receives imaginary power. When the imaginary power stops going to the latch coil, it does nothing. Rather than writing a 0 to memory, it just does nothing at all. Conversely, down here at the unlatch coil, when I send imaginary power to it, it actively writes a 0 to that memory bit, in this case element 0 bit 0. And when I stop sending imaginary power to it, it does nothing. So this is a little bit different from, like I said, a normal OTE coil instruction. Let's see how this works. I'm going to turn on my start switch, pushing my start switch here, and that is going to send imaginary power to the latch coil, which sets that output bit to a 1 status. When I take my finger off the push button, that goes back to its normal status, and notice how this bit remains set. We see the red power flow going through here, even though no power can make it through this contact. We see the red highlighting, which indicates the status of that output bit. So in this case, it has now been latched into the on condition. In order to unlatch or to reset that bit in the PLC's memory, we need to send imaginary power to the unlatch coil. So briefly pushing the stop button over here sends imaginary power to the unlatch coil, and that takes the output bit and resets it to a 0 status. So pushing this switch sets it, turns the motor on. Pushing this switch resets it, turns the motor off. Looking back at my PLC, see how this works. Here are my 2 switches. They aren't really push buttons, but I'm going to treat them like they are. So briefly pushing this energizes the motor. Briefly pushing the stop de-energizes the motor. So I have a latching system, a latching stop-start motor system. Of course, kind of begs the question at this point, what happens if I push both at the same time? What happens if I push both the start and the stop switches simultaneously? What's going to happen? Well, examining the program here, we see each one of them going to its own coil. The coils are both addressed to the same bit in memory, one of them being latch or set coil, the other one being an unlatch or a reset coil. So if I were to activate both these contacts here, sending imaginary power to these 2 coils, seems like we have a bit of a contradiction. One coil sets the bit to a 1 state, the other one resets the bit to a 0 state. Which one wins? Well, let's go over here and turn our switches on and see what happens. So I've now activated both my electrical inputs to the PLC. These 2 contacts, which remember are read instructions for those 2 bits, are reading both the bits as being set, sending imaginary power over here, but over here we don't see a whole lot happening. It would appear that our output bit is indeed a 0, and let's go over here to our PLC and see if that's the case. So I have both inputs set right now, are energized. You see both of the LEDs for the inputs lit up, and the output is not, so my motor would not be running. Let's understand why this happens. Looking at this, there's a definite sequence to the scanning or the execution of the ladder logic program. It reads from left to right, top to bottom, kind of like reading words in English written on paper. So the first instruction in the PLC's execution is it comes to this contact, which remember is a read instruction. It reads the status of that bit, sees that it's set to a 1 condition, sends imaginary power over here, and it latches that. So it writes a 1 condition to the output bit. So that at first would seem like it would turn the motor on. However, let's see what happens in the next instruction. Coming over here, it reads the status of this bit, it sees it being a 1, sends imaginary power over here, and this writes a 0 to the output bit. So that resets the motor and turns it off. Now you're probably wondering, why doesn't this make the motor turn on, off, on, off, on, off, on, off? Well, what's happening is it scans through the program. The PLC is actually turning the output bit on, off, on, off, on, off, on, off, but we don't see the motor chattering on and off because of what happens after the program is scanned. After it does this and scans the program and executes all the instructions, only after it's done with all of that does the PLC actually go through the output word and transfer those bit statuses to the real electrical outputs of the PLC. So even if this output bit, element 0, bit 0, is toggling on and off during the execution of the program, that doesn't actually show itself to the real life wired output until the program has completed its scan, completed its execution, and then the PLC writes those bits or transfers those bits to the real world output. So what the motor actually does is what this output bit is at the end of the program, not during, but only at the end. So the input scan, PLC reads the hardwired electrical inputs and puts those bit statuses in memory. The contacts read those bit statuses, sending imaginary power over to the coils, writing those bit statuses, but only after the program is done do those output bit statuses actually get transferred to the real world output. So we don't see a chattering effect on the motor. We see the motor is off because this is the last instruction in the program. So it'd be kind of interesting here if we were to modify our program a bit. I'm going to go offline, and what I'm going to do is change the order of these two rungs. I'll take this rung right here and move it there. So I now have reversed the order of the two rungs. Now the stop comes first and the start comes second. This is going to have a profound effect on how our program executes. So I'm going to download this to the PLC. Turning both my switches off to start off again. Change back to run mode and go online. Now here, both of my switches are off, nothing's going on, so right now I'm going to take both my switches and turn them on and see what happens. Both my switches are on, and they're sending imaginary power to the respective coils, but now we see the highlighting lit up on both of these output coils, the unlatch and the latch. And we might ask ourselves, what's the motor actually doing? Well, we go over here to the PLC, and we see these two switches are on, and the motor is actually on. Now, why is that? Because last time we had the two input switches on, and the motor was not running. So over here, we see why. Again, keeping in mind the scan order of the program, the first rung that gets scanned is the stop instruction, or stop bit. So it sees, yep, that's a 1, sends imaginary power over here, unlatches or resets output bit 0. So at that point, the output bit is 0. It comes to the next rung, it reads this input, the start switch says, okay, it's energized, and it sends imaginary power over to the latch coil, which writes a 1 to that output bit. And since this is the last write instruction to that bit in the program, that's going to be the actual status of the output bit at the end of the program's execution. So at that point, when the PLC takes the output bit and transfers it to the real wired output, we see the motor turned on because that was the last instruction. But meanwhile, during the execution of the program, we actually do have a flip-flop effect in this output bit, starting being a 0 condition and then going to a 1 condition, because these two rungs are essentially contradicting each other. This one is resetting the bit to a 0, this one is setting the bit to a 1, but since that is the last instruction in the program, that's the status that gets written or transferred to the output of the PLC.